So, that was a nice coffee break. So, and dear friends and colleagues, let's start our next session, which I have the great pleasure and honor to share. And I also have the great honor and pleasure to introduce our next speaker, which is Mark Lindsay from CSIRO from Australia, from Perth. And he is giving us a talk about the map is not the territory, geosciences in the AI era. And I'm very much looking forward to your speech. Mark.
Thank you very much. Good. Thank you for the introduction and thank you for the welcome. And many thanks to the conference organisers for inviting me to come along to this. I was very excited for a long time about being here. I'm sure it's going to be great. So CSIRO is Australia's national science agency. We have a number of business units, one of them being mineral resources, and mineral resources has a number of programs which cross the minerals value chain, starting from exploration and discovery, mining, processing, characterisation and sensing and sorting. Just as a background about myself, I am a geologist by training, structural geology. Being in Australia, geophysics is a necessity because there's not much outcrop. And of course, getting into 3D modelling, uncertainty, and data science. Now I'm quite a generalist, probably not very good at any one of those things anymore, but we truck on. So this talk, well, at least the byline for this talk, the map is not the territory, it's not mine, it's something you've probably heard before. But it was coined by Alfred Korzybski. Apologies for the pronunciation to our Polish audience members. But Alfred was a proponent for something called general semantics. And this is back in about the mid-1940s. And general semantics largely is around the fact that our version, or reality as it is our understanding of reality is restricted by our own perception. So from our five senses, and our ability to communicate our perception, either orally, visually, and I guess these days, digitally. These days, of course, those restrictions are becoming less and less. I think we've got more and more sophisticated algorithms. We have more and more data that we can feed into those. And that what we hope is that our understanding is getting closer and closer to what the reality really is. However, I think one of the things we need to be careful of is our emotional attachments to the models that we make, and that rather than tuning our models to reality, our reality to our models, we are actually tuning our models to reality. I thought it was a great idea to put some of the discussion topics in the program, so well done to the conference organisers, and I'm hoping that at least some of these four topics here I'll be addressing in this talk. Some food for thought. People can throw tomatoes at me if they don't agree. But underlying all of this is thinking about how our geological maps can be used as features, or parts of those geological maps can be used as features for AI, but also creating geological maps and models using AI. So inputs as well as outputs. Just a bit of background to the work that we're doing at Minerals 4D Initiative. These are some of the wonderful people I get to work with. One of them's here, which is Fabian Leal, who's giving a talk tomorrow. And our mandate is looking at the mining value chain, or the minerals value chain, including exploration, and trying to understand, I guess, the scaling issues that we have, because it's fundamentally a scaling problem across time, space, as well as our properties, but also how we propagate uncertainty and knowledge through that, retaining that knowledge and understanding when we do scale things, what uncertainties we incur. So to start with, this paper was produced from iron ore prospectivity study that we did back in 2022. Some of the preliminary work I was presenting to a number of industry people. So the workaround was, a typical prospectivity study, which is a data fusion exercise. We use a lot of different features that represent different geological phenomena. Some of them process-based, some of them structural, geophysics and so on. But what we're looking for is iron ore prospectivity up in the Pilbara region, very famous iron ore mining district. And it's predominantly hosted in the Brockman and Marramamba iron formations. This is well known, and there's not too much uncertainty around that. Some of these features that we use, there's quite a few that we felt were necessary to build a reasonable model. Things like magnetics, radiometrics, maybe radiometrics represents different levels of weathering. We have silica content in aster from satellite. We also have some structural, you can use the cursor, structural information in terms of dip angles, distance from faults and folds. We even built a 3D model, which we use to determine isopack thicknesses of different formations, and stratigraphic thicknesses and so on. One of the exploration geos in the audience just looked at all of this and went, this is all too complicated, why don't you just use the geologic map? Okay, which is a fair question. I think he was thinking of Occam's razor. It's like, why are you overcomplicating things, throwing in more data than is needed or more features than is needed, too much noise. You know it's hosted in those ironstone formations, just look for those. So I thought, well, that's actually not a bad point. So I did a literature survey of a lot of the prospectivity studies that are out there. How important do we think, or do people, just by weight of evidence, think that geologic maps are? And this is just a number of different things that I thought people would include or not include in their studies, things like lithology or geophysics, remote sensing. You can see that 10 of them use 3D models, if we look from the fourth one down. Geochemistry, 69 papers of the 126 were used. Only one of them did any ground truthing. Interesting. But every single paper had the geologic map. Okay. And this shows, I guess, that there's a very high esteem for geologic maps. Quite rightly, they've been around for a long time. They've been very useful, still are. But also seem to be the gold standard in terms of geological representation. And the purpose of this study, initially, as it evolved, was to say, okay, this is one person's opinion on what we need. What if we take a number of different studies that have been done talking about iron ore models, or genetic models, and subject them to a random forest prospectivity style, prospectivity model. And so we've got Thomas Angerer, Paul During, and Caroline Perring, who all have slightly differing opinions on what processes are involved in terms of iron ore formation. And do feature selection from that group I showed you from before. Not all of them agree on what is important. Run the models, and then you find that there's quite a few differences in between the predictions, spatial prediction, as well as building some models, just throwing all the features in because we can't decide, or throwing in as little as less as possible with a parsimonious model. For the purpose of this presentation, really, is just trying to understand what the relative feature rankings from the variable importance were. And just talking about the geologic map here, yes, everyone included it, everyone felt it was important, but it's not always the most important. And in fact, in some of these models, the geologic map is not the most important at all. And you can see that, yes, it does make a difference in predictions depending on who you believe, in terms of which genetic model is correct. But from my personal view around the geologic map, it made me think, well, okay, if it's not the most important, and say I go against, I guess, the general feeling towards geologic maps and not include them, what happens? So we ran that experiment, removed the geologic map from these models, or ran a model that had all the features except the geologic map. And as we can see here, this is just classification scores from the training and the validation of these models, and it performs very badly. So while the feature rankings say that geologic map's not important, the classification metrics say that it is, or at least not including it is detrimental to the map, the way the model works. And once you plot the different, so this is just a model with all the features included. When you take the geological feature away, it becomes very noisy. And in fact, if you presented that to an explorer, they'd say, that looks like rubbish, we can't use it because, in fact, a lot of these areas through here, especially through here, are just implausible for iron ore mineralisation. So if nothing else, while it's not determined as the most important layer, it's a very good plausibility filter for these kinds of studies. So the geologic map, not only does it give complete coverage, but it makes sure that the rock types that are contained in the map filter out basically silly locations for iron ore mineralisation and guiding people to the right ones. But we did encounter some problems with looking at some of these geologic maps when we were running this study, and this is either as just basically going through and debugging the model, and also around building the 3D model. And you can see some here. So Charlie did mention the measurement uncertainty here. This relates to this a little bit in terms of, say, GPS error, about where the boundaries might be based on the fact that the GPS might be slightly wrong. But it's mostly around the epistemic error, which is the lack of uncertainty, and how we join the lines between our observations. And epistemic error can also relate not just to the position through interpolation of these boundaries, but also what the boundaries actually are. So, but in this case, you can see here we've got in the world imagery, we can see this is Tom Price area, very famous, one of the first iron ore mines discovered, or iron ore locations discovered in the Pilbara, still being mined today. These white lines are the boundaries for the Maranamba Formation in blue. That's the geologic map says here, and it covers most of these pits, but not all of them. So there are some pits that are outside of that, and that's from the 100k map. You go to the 500k map, and it's even worse. So a lot of approximations have been made to produce a 500k map at that scale. So in all fairness to the Geological Survey, who produces really good maps, this is not the purpose of what their 500k map was for. And not even the 100k map. They weren't thinking that people were going to be doing these kinds of things when they first developed them. But I guess that's my point, is that if this isn't fit for purpose for this kind of study, what can we do about it? There's the other thing that's also important, and Charlie mentioned this as well, is that these map polygons, single blue colour, don't really reveal the property distributions, I guess in this case the magnetics. And this might show you the location of hematite in the dead magnetic areas versus magnetite in the elevated magnetic areas. But these problems with geologic maps, and I guess their reliability, have been well known, of course, to geologists who have been doing mapping for a long time. And this is a geologic map from the Kimberley region in northern Western Australia, Noonkaba. This is a 250k map. And it's got a really nice little inset in there, which is a reliability diagram. And what this reliability diagram tells you is where the detailed surveys have been for gravity and reconnaissance. And where detailed reconnaissance, geological reconnaissance traverses and air photo interpretation have been conducted, as well as where some haven't. So it tells you basically reliability in this entire map of the geologist's interpretation. So this is 1981. Okay, this is quite a long time ago. But do our digital representations of these maps have these reliability diagrams now? No, they don't, unfortunately. And this would be really useful to know, especially for someone like me who's jamming them into a random forest. So one of the things we can do is there's something called the Integrated Exploration Platform, which is a platform provided by the GSWA, and it was part of a linkage project through the ARC. And it leverages off a whole lot of techniques using lineament detection, phase congruency, phase symmetry, phase symmetry. And people are probably familiar with these techniques. They've been around for a long time. And the idea for this one was not so much to use the edge detection as a way of saying these are all the things you need to include. Let's do the whole thing automatically. It was really to say, if you have an interpretation, how well does it match to these edges? And if you're thinking about, say, where your dikes might be, you might look at the positive phase symmetry, which is this map down here in the bottom left corner. If you're looking for contacts, you might use the phase congruency, okay, top right corner. And the same thing for negative phase symmetry. You're looking for faults, demagnetized zones. You might be starting to look for these kinds of things. And this is what it looks like against an interpretation I did of the central part of Western Australia, the Urea Basin. And this is just the gravity signal, looking at strength of evidence with edges. And basically, all of my interpretations are given a score through this edge detection process. And the strength of evidence for gravity against edges, meaning possible geologic contacts or so on, high, medium and low. Okay, this is quite useful to know. Say you want to weight these things for any downstream modelling process. It's also a good thing for me to go and double check what's going on. But then I might not be looking for edges, I might be looking for valleys in the DEM. Okay, so any grid can be added into this, not just gravity, not just magnetics, but anything. And you'll notice that, of course, all of the different evidence levels change because I'm looking at something else. You know, strength of evidence with valleys. Same thing for magnetics as well. If I'm looking for dikes, for example, for faults, this area through the middle here, high confidence for those, not so much for these ones here. So what do we do with this kind of information? So what you can do, and this is just to show, yes, you do get a quantitative value of your confidence in your interpretation. So that's the bridge score from the RTP magnetics, valleys, edges, and there's a DEM and so on. And objective, complete and repeatable, I think, which is a really important fact, that we're not having to add confidence values according to how we feel during the day. Is it the morning, is it the afternoon, are we tired at the end of the day? This kind of thing is repeatable and objective. And what we might be able to do is to look at, say, 3D model uncertainty analysis, because if our fault is uncertain, of low certainty, and here's our low certainty geologist over in the right, the top left there, we might then think there are multiple realisations of the same fault. So this fault is dipping at 75 degrees, maybe it's dipping at 65. Or maybe in fact it's somewhere else and dipping at another different angle for even lower certainty. And of course that would say the same things, multiple realisations of the same contact. We can move around a bit. Okay, and of course because we've got multiple realisations, we have multiple models, and we can generate a whole ensemble of models to see how broadly our models vary given the data that we use to build them. And we can jam them all together, see which parts of the model vary the most, and see which parts of the model vary the least. And this is just a heat map showing where the variation is high, so the hotter colours being high and the cooler colours being low. And we can also do a big spin around, which we'd like to do with 3D models. Looking at all the different surfaces, greenstone belts, faults and so on. There's an inlier in there as well. And then we can produce this overlay, and that tells us where the rubbery bits of the model are, particularly in the bottom left corner there, bottom right corner, which interestingly is prospective for gold and nickel because there's a greenstone belt lying under there. So that could tell us about data acquisition. This then, of course, is about position of uncertainty, position of faults. What about the classification of faults? So what are they? And we've built something called the Noddyverse. Noddy is a kinematic modeler, which you are allowed to put, what allows you to put in a whole set of tectonic events, like some conformity, tilts, folds and faults, and using the same, changing those, the sequence of those things around, you get a different realisation of what the geology would look like. The other good thing with Noddy is that you can forward model the geological model that you get from that using gravity and magnetics, and you can do that a lot and provide a training set of both gravity and magnetic realisations of a whole lot of different 3D geometries which are tagged with the tectonic sequence that produced them. And this is the paper there. This is a data set that you can download. And one of our students, Marta Brashidafard, who's just completed, hopefully this will be published soon, has used this in an area in southern Queensland called Boulia to try and look at the seismic profiles, the observed gravity data, using a multi-view convolutional neural network to try and identify what this flat-lying structure that you can see in the seismic is. Now, the nice thing about this is that it successfully identified it as an unconformity, which is not that surprising given it's a basin interface. But, and with probability, so it's 97% and it offers other probabilities as well. So it's not just giving you one answer, it's giving you the other options and their relative probabilities. But the fact that it identified that properly means that other folding structures that were seen in the seismic, with less probability, we have some confidence, at least, knowing that was at least somewhat plausible. And moving on to, I guess, some of these pesky boundaries that we're talking about in terms of scaling, I'm advocating for something, you know, I've got this aspirational borderless worlds title here. But there is some research coming out now, some results coming out now, especially from the GSC. This is the some of the work that Christopher Lawley has done, using natural language processing to produce these maps based on extracting the rock descriptions from, I think it's 30k to 30k maps, a compilation of maps from 30k up to 500k scales. And doing that for the North America and Australia as well. So not relying on polygons anymore, but really plotting these different rock types out spatially, which I think is a more scalable, at least certainly interesting for me, for the minerals value chain representation of the lithosphere. And our next speaker is going to talk a little bit about that, so I'm quite excited to see what's going on there. And of course, Charlie's work talking about looking at property distributions with their uncertainties across, you know, I guess aspirationally across the entire globe. And I see this also as a really important aspect that is scalable and also includes an uncertainty assessment. You know, very enthused by what is being presented at this conference, and I'm hoping that you know, these questions around scaling, boundary identification and classification, you know, we're providing some solutions here. And I'll leave you with my final thoughts. All right, thank you very much.
Wow, thank you very much for this very interesting, thought-inspiring talk. So we have time for a couple of questions. About now. Yes, please.
With really key map boundaries or some of this uncertainty, do you think there'd be a lot of, like, a large gain in accuracy by, like, fuzzifying some of our, like, binary rasters or including that kind of information in there?
Yeah, I think, well, it's about representativity. So it's making sure that how much do we actually know before we feed into an AI who doesn't understand that those map boundaries, as geologists we know that a map boundary is movable depending on who you ask. An AI doesn't, unless you actually give it some sort of a weighting criteria. So yes, I think something like that would be helpful. Yeah.
Yes, please.
Well, great talk. I wanted to dig into the uncertainty aspects that you mentioned in the middle of the talk. What do you think the value is of including a full uncertainty map for the whole area alongside these mapped outputs? Because when I was doing my PhD, I was working with Matt Cracknell in Tasmania, and he showed that some of the default boundaries that might be undercover in Australia and in the Broken Hill area would be shown up mainly the model itself was uncertain in this area, not because the data was necessarily uncertain, but the eventual output map was saying, well, actually, I can't classify this as a granite versus a mudstone or whatever it is, because there's alteration there, but he didn't have data on alteration.
Okay.
The uncertainty of the model said there's something going on there, and it is a geological process.
Yeah. Okay, so there's some anomaly that is there, which is present, but is not included in the model, so it's hard to then provide an uncertainty assessment.
Then gave you something to interpret as a geologist as well.
Yeah, well, that's right. Yeah, and I think to bring it to, I guess, the geophysical realm, maybe you've done a geophysical inversion, you see that your inversion has some anomaly that is not honoured in the original model, and it's continually trying to fit that in. And I think there's a lot of work now, some really interesting work around transdimensional geophysical inversion, where these new anomalies are being initiated as a test case and running through a whole lot of different scenarios. I think that's quite exciting. But it also, because you can do that, you can see how many different tries you need to resolve against that anomaly. What I showed is not sophisticated by any means. I mean, there's other speakers who are talking about uncertainty in 3D especially, which will show some really cool stuff. Very excited to see that. But yeah, absolutely. I think there is that epistemic uncertainty, is that we have never included absolutely everything in our model before we subject it to validation against or testing against some other independent data set. So I guess we always have to keep that in the back of our mind. Yeah.
So there was Vasily, and then everybody else can park their questions until lunchtime and then grab hold of Mark too.
Yeah, please.
Thank you, Mark. Great talk. Specifically like your discussion about feature importance. I wonder your experience, this feature importance ranking, does it depend on the method, the machine learning method used, or the ranking is consistent across the methods, so we can just go with the simplest and computationally efficient, you just select those most important features?
Yeah, and that's a really good question. And yeah, there is some sensitivity to the rankings, to the method. With this particular implementation, there were some metrics that the bagging error that will tell you whether or not those rankings are robust. Of course, you can do cross-validation that will also show you how variable your performance rankings might be. Of course, QA/QC, looking at these performance metrics, you've got to double check that, yeah, over a number of runs, those rankings don't change a lot, even with the same algorithm. But yeah, it could be worth running it through, say, maybe a different style of decision tree, XGBoost or something, I don't know.
So thank you very much.
Thank you.
That was